Dear students, welcome to the fourth lecture on cooperative communication systems. Today we will continue to talk about cooperation in wireless networks and mobile phones. Today it's very relaxing because we just go through some examples showing what kind of cooperation we have already implemented to give more motivation on this topic. Okay, last time we talked about different forms of cooperation, right? From forced cooperation to altruistic cooperation, technically and socially supported or enabled cooperation, thinking about the terms incentive, benefit, and cost with a relative factor R, and still we are looking into these four factors. In the cooperative mobile clouds, we distinguished the resource sharing and the capability extensions and went to some IPR related to mobile clouds. And last but not least, we looked into the cooperative reliable multicast mobile clouds, which we will continue in the later lectures more in detail with mathematical branch route and analytic models for that. Today, let me continue about the cooperative wireless networking part 2. And what we would like to do is first to look into energy consideration in mobile clouds, look into economic benefits and market potential of mobile clouds, and then look into cooperation in all 7 ISO OSI layers, right? Going from the top to the bottom and coming example by example. There are some examples named here already, but I think you will see them while we are going through these examples. So first of all, let's look into the energy considerations. And that's quite interesting because it will tell us something about the cost, right? So in a mobile phone, beginning of 2005, there was the starting of the smartphones, and the problem was more or less to understand how much energy such a device could manage. And the early phones, they used around 2 watt, then we had something about 4, and then new forms could even go higher than 6, and more than 6 would require cooling on the device. Currently everything is passive cooled, so you don't have any ventilators that you can hear. And here you see the different functions that will eat up a certain amount of the energy. This is not quite concrete and quantitative. So on the right side, you see this for one of the first 3G phones, the power use distribution, when they were using around 3 watts. So 0.6 watt was for the application processor, 1.2 watt for the wireless modem, and 0.4 watt for the display backlight. So there are other things like speaker, camera, Bluetooth, and others. And the question is, this was a plot by Nokia, and we wanted to look into this more in detail. So first of all, what you see here is an N95 Nokia model that we made photos with the thermal camera, and you see once it's idle, it was 28.5 degrees Celsius, and once you switch on the wireless cellular communication, you see already you increase it by 8 degrees, and there are some very hot areas. These hot areas is mainly the battery and some metal around it, and it's not that the battery is really producing the heat. The heat comes from different sources, from the chips mainly, but the heat is then dissipated into the battery because it's some form of liquid that can take the energy and the heat, and that is interesting how such a concept is built. This is one of the things a phone should do, manage the heat on the device. Good. What we did is by we, that was a time in Aalborg University. You can still see here the link from the mobile device group that we had, and we looked into different wireless communication technologies, and we looked into the energy per bit over the bit rate you transport something. So what you see is a certain tendency from the left top to the right bottom, and for 3G, 3.5G, so this was quite a wide area range. You can go from 100 kilobit per 1 megabit, more or less. And you see the higher the data rate, the better is the ratio energy per bit. I mean, the higher will be also maybe the heating problem on the phone, but if you look at the energy per bit, this is going down. If you look at the 2G, they had not so much data rate, but you see it's more or less a line that is a little bit shifted in parallel to the 3G one. Is a little bit lower. That has to do with the chips that were used with the 3G technology. As an extension, interestingly, from the 3G, you see the wireless LAN, which can have um, way higher data rates, but also you see the same degree. And there's a little bit thing down here. This is Bluetooth. But you see also it's way down there, so that it's way better for energy per bit. And these things we need later for cooperation. The same power over the bit rate, the power values that they're using, it's more or less the same stuff here. For Bluetooth, we used 2.0 with enhanced data rate, and anything else you need to know for these plots are given on the data sheets on the given link. Now, we looked a little bit closer into Bluetooth, and we looked into what is if Bluetooth is off, then we switch Bluetooth on, then we made Bluetooth in the connected idle mode, Bluetooth discovery, Bluetooth receiving and sending. And then you see sending is way and receiving is way bigger than, for example, just Bluetooth on, right? If you keep the connection, there's a little bit on, but just having Bluetooth on did not eat up so much of the energy. And that you see here, once again, the difference between these two values. So a lot of people wanted to switch off Bluetooth to save energy. There was not so much to win. It's more about really be connected to devices that you need, then you can transport data, and if you don't need it anymore, just disconnect. And for Wi-Fi, we had the same for connection, disconnection, idle, and idle in power save mode. Then you saw that connection also eat up something around 900 milliwatt over here. If you look at Bluetooth, it was only half of it. And you see Wi-Fi has way more for it. But if you look at the energy per bit, that is way better than Bluetooth. Also here you have the link if you want to see the whole data of our measurements. Now we looked into the display, and interesting is more that different colors like white background, black background, and screensaver, the different values for the light intensity level that you can really control on your mobile phone. And you see that the white background is eating up way more energy. That's still the fact today. So a lot of people are using darker colors to save a little bit of energy. And here you can save something. If you compare it with the 900 megawatt for the Wi-Fi, here you have something like, if you have a white background, 500 milliwatt, right? So that's interesting. Then you have impact on frames and for how many frames per second are changing. This is quite linear, but the intensity plays a role here. Okay. Then we looked also into memory and into the computing. One for the computing, you see the CPU usage. The more you use it, you have this characteristic of the curve that was a little bit unexpected, because as you will see later, all the CPU that we know of has a different form where you would get way better percentages of or less power consumption if you halfen or quarter the clock rate. For the memory, you have different memories available on the phone, right? Something like a memory card and flash memory. And if you look at these different types here, D, E, and C, you see the energy consumption in joule for 1 megabyte of storage differs really dramatically, right? So just to know how to store data can have an impact on your power consumption. If you think about power consumption in mobile phones, interesting quote here by Steve Jobs, who said in the beginning of the iPhone, so that was the time when Apple could not even get more apps on the phone. The new apps came with a web browser, and even though 3G chipsets were available, the iPhones only had a 2G chipset. And Steve Jobs said at the time the 3G chipsets that are available to semiconductors work reasonably well, except for power. They are real power hogs. So as you know, the handset battery life used to be 5 to 6 hours for GSM, but when we got to 3G, they got cut in half. Most 3G phones have battery life of 2 to 3 hours. And this is even a positive way of looking at it, right? So at the beginning, some of the 3G phones, they had already 2 battery packs, and you could change the battery in case you need it. And in case of Steve Jobs, the reason why he did not want to go for 3G is this operational time. And the operational time is important for how often he can sell something on iTunes, right? So what he really meant is longer battery times allows the customer to download and enjoy more iTunes, and this means money. And I do not care if you wait some seconds more to download it. So he was really not interested in higher data rates because there was nothing on his phone that would benefit from higher data rates. Now, if you look into energy consumption, there are 2 interesting trends, or 3 interesting trends. The Moore's law said that integrated circuits will double in performance every 24 hours. And Nicholas Wirth said once, software gets slower faster than hardware gets faster. So you see that there's one end, the hardware is trying to get faster, but even the software is getting slower and slower because more complex. And if you look at these numbers, like 24 months doubling the performance, you have to understand that the energy capacity is only doubling every 10 years, right? So energy was back then a big problem, still it is. In some of the airports, for example, you can get energy for your phone for free. In others, you have to pay for it, right? In the beginning, you paid something like $3 for 30 minutes charging your mobile device. That was quite interesting because for $1 in the American airport, you could call back to Europe for $1 for 30 minutes. So you paid 3 times as much in charging your phone than just calling over a public telephone cell that was still available back then. Then different ways to extend the battery life was really by such better AA batteries that you could put into such a box and then plug it into the Nokia phone. This worked back then. I think today nothing like this is available. You have the battery packs that you have to charge because you need more power. Or there were other ideas like to pee on your battery, right? And PEEP will be transported into power. So these are not the solution we are looking for. So what we would like to do is to reduce the energy consumption by this kind of cooperation. Here you see different architectures that we will talk about in the future. We have a cooperative group with a number of users talking to the access point. The access point is connected to a router. To the same access points, you could even have non-cooperative users, and then they will go to the service providers and ask for certain contents, right? And you're not alone. There could be other cooperative clusters around you, and they're also competing with you. Then the cooperative cluster, we said that we need the same common short-range technology. The cellular connectivity does not have to be the same. It could be 2G, 3G, 4G. There was a time there was even DVB-H available. So the question is, do we need the same cellular one? No, that's not needed. And then we have different kinds of service versus transport ideas. So you can have something like unicast service with a unicast transport. So everybody gets its own service, and then you can exchange additional information. That's pretty hard to find a good service for that. If you have something like multicast, so everybody gets the information also for your neighbor, and then you exchange, that's quite interesting for in case some of them is losing connection to the overlay services, then you can help each other. Then you can even have a unicast transport, and they exchange fully over here, or a multicast service with a multicast transport. So 4 different scenarios how to cooperate. But you will get examples for this later on. Good. Now the question is, why should we cooperate? We only looked at the users, but there are more, right? So the customer is one of the things that we can optimize with cooperation. But what about network operators, mobile manufacturers, or service providers? So all these 4 have a certain say into cooperation, whether it will start or not. And here's a simple example that we did back in the time where we said, think about first about one user that would take a service, low-level service, and pay for it only, let's say, one money unit to the service operator because the service quality is low. And also the network operator will pay for it because the sources you're using is not that big to get this small service. It's different when you say you want to have high quality service, then you will pay more to the service provider, but as the data rate will increase for this service, you also pay more to the network operator. And what would happen in a cooperative cluster? So if you, for example, get the high quality service, right, the 3 over here, you pay for it, everybody will pay for it. And now the data rate, as we are sharing the medium, we will only pay a third of it. So now the network operator will not benefit from that because he will say, hey, I'm not only get a quarter compared to a third compared to the non-cooperative one. On the other end, maybe these devices would not look at the content at all if it would be lower quality of it, right? So here you see a little bit of service provider, network providers, and the customer. The other thing is there's more market potential, right? So if you're a user, you have some inner circle planned activities, and you would see certain services that are given in the network. Once you're looking around what others are looking, because you're looking for cooperative partners or they are looking for cooperative partners, they might advertise other services they're interested in and maybe they will join. So therefore, this cooperative idea could have an impact on the dissemination of the service itself. Here's one of the things that we invented back then, where we said, hey, here is a group of people that watch MTV, SPN, News, somebody of doing BitTorrent or playing Warcraft. So here we are missing one, here we are missing two people in order to make the service really reliable. And while you see the services, you can even join these services. This is the kind of new market potential we are talking about. Now, if you look at the mobile device complexity for the manufacturer, so think about 3 classes. You have a low-class device, a mid-class, and a high-class device. And this is a trade-off between service and complexity. Only with the high-end devices you can have also good services. But what if we allow low-end users or mid-class users to cooperate to also to get a higher service? And then you would have low-end devices also allowing for services once they cooperate. So the high-end class device would always have the highest service whether they're cooperating partners or not, but the others could maybe make use of devices around them. And normally you have this classical linkage between air interface and display, air interface and display, and this linkage is broken if you think about cooperation, because then you can only need a very good display and a smaller air interface. Good. We will see how this works. If you bring this together for the customer, the network provider and service provider, manufacturer, and you look at the certain advantages that they will face, then most of the time you see the word money, right? Money drives the world, so this is clear. And if you have other things like standby time for the user means also more money for service operators, right? And if you can find out that you can increase the stand-up time, most likely people will buy your device. And here you see the benefits for cooperation for the 4 different players. In the next, I would like to talk 2 slides about the wireless technologies. It's important to calculate later the benefits and cost. And here's an old picture that we used back then, but still it's valid. It's about data rate and the range. And you see here on the right, the green one are the cellular technologies. Now you can add LTE and others for 5G here. And then you have others like short range like Bluetooth advanced data rate, 802.11b, IEEE 802.11a and G, now A and C, whatever, it goes up, right? But it's interesting there's a relationship between data rate and range. And also data rate that has an impact on the power consumption. We will come back to this later. Now, if you have multiple short-range technologies, you can even use them as a shifting gear idea. So why always using something like ultra-wideband Bluetooth or Wi-Fi and the highest way? Because this will high data rate, but you will also use a lot of energy. Why not using other technologies just to find out where you are, in which scenario you are? For example, you are the RFID wake up for to say, oh, now you are in the airport. Ultra low power Bluetooth to identify services and other cooperative partners. Bluetooth to exchange some contracts for cooperation, and then later, if you exchange really data, going to the Bluetooth where the energy per bit is the lowest, right? But just switching this on will eat up the battery. But then you are in the phase of retrieving some services and everything should be fine. Okay, with that, I would like to start with the 7 layers of ISO OSI in our next part.